Good morning, everyone. I work for Photonics Bretagne, and today I will present you a subject of hyperspectral microscopy based on the ONE-PIX method. So Photonics Bretagne is a non-profit association, located in Lannion, in Brittany, in France. It's composed of two parts, a cluster, including different industries, research institutes and academics, and a continuing education. The aim is to promote photonic sciences to a wide range of audiences, from the informed to the general public. And the other part is the research and technology organization. There are two different teams. The first one works on special optical fibers and components, and I worked on the Biophotonics team. So in the Biophotonics team, we develop photonics technologies for life sciences, up to TRL7. So TRL means the technology readiness levels. So the number 7 correspond to the demonstration of the prototype system in the operational environment. So we also support company in using photonics technologies. So we start from an idea or project, and we go across different process, the proof of concept, the hardware, so making the setup, the optical setup, for example, or with using electronics. Sometimes we need to use a software to synchronize different elements. And the end is the industrial technology transfer. So we transfer the project to industry. So we have different fields of application: cultivation, aquatic resources, farming, agri-food, and biomedical. So the ONE-PIX principle. It is an affordable hyperspectral camera based on the single pixel imaging. So affordable because we don't use a real camera. It's just a single point that gives us the spectrum. And from the spectrum, we can apply an inverse transform to get the image reconstructed after. So we have a projector that is our active illumination. We project some pattern. Each pattern, for example, here it's Fourier, the basis of Fourier. We have a frequency for each pattern that we project on the sample. And we record the intensity of the pattern superimposed of the sample. So we measure the intensity thanks to a spectrometer, and this spectrometer gives us the character of hyperspectral because it is measuring the intensity in function of each wavelength. So after that, an algorithm of reconstruction can reconstruct the image. On the right, we can see the different pattern that is projected on the sample. It is constructed the spectrum, pattern after pattern, and we can reconstruct the image after. So we may wonder if we can adapt this method for the observation of micrometer scale samples. So we use the color illumination to shape the incident pattern on the entrance pupil of the objective. So again, we have the projector. We have a set of lenses that fit the pattern. We use the Hadamard basis because for the Fourier basis, we had a problem. In fact, the grayscale is not good for high spatial frequency with the projector. So we use a basis that use just black and white colors. It's easier to project. And we collect the intensity resulting by the association of the sample and the pattern. The camera just here is just here for the focus of the objective, to get the sample in the focus of the objective, but it's not used for the reconstruction. And then across the beam splitter number 2, we have the lens L3 that focus the light on the fiber, and we have the spectrometer that records for each pattern a spectrum, that is the intensity in function of each wavelength. And the software synchronize the spectrometer with the projector to have one measurement per pattern, and after to reconstruct the image. So we can make a complete acquisition and to change some parameters to have a whole acquisition. So what are the performance of this setup? So we use MIR to have the information of the resolution limit. So we have an intensity profile at a special frequency. And we had the result of 9 micrometer using 0.44 numerical aperture. So the spectral range go across from 300 nanometers until 750 nanometers. And the spectral resolution come from the spectrometer, and the spectrometer is limited at 2.1 nanometers. So each 2.1 nanometers, we have an image of 2 dimensions, so 2 spatial dimension. And the spectral dimension, we have a lot of wavelength, so every 2.1 nanometers. So the first result we had was copper. This sample was used to attest the spectral information of our hyperspectral microscope. So on the figure 8A is the image from the camera. So it's to compare with the reconstructed image to see if we saw the same elements. So the figure B is the reconstructed image with false colors. And the C is the segmentation, within purple the cluster of copper. So in D we have the graph with our normalized spectrum of the copper sample from the purple cluster. So in purple, and we have also the literature in red to make a comparison between our results and the literature. So we can see that the evolution of the spectral reflectances are the same. And we can see that at 550 nanometers, there is an increase for both spectra. And it is from the signature, the spectral signature of the copper. So it is typical, and it is encouraging to continue for different samples, like biological samples. So to continue with another sample, a biological one, we try to image microalgae. So we try to make the spectral discrimination of 2 different nitrogen-dependent microalgae. we can see on this image, so it's a conventional microscope, we see two different algae, but it's not really clear. And with the hyperspectral microscope, we make a segmentation and we see that we have two different clusters. So the first one in green and the second one in white. So with the spectral information, we can discriminate the two different algae. So we make the segmentation using a principal component analysis and a K-means clustering, that is an algorithm. And so we have the hyperspectral microscopy spectrum compared with the reflectance spectroscopy, and we can see that is the same. After that, we tried to image minerals. So the pink granite that it comes from the coat of rose granite near Lannion. So at a macroscopic scale, we just saw granite, a rock, but at the micrometer scale, we can distinguish different phases in the different mineral phases in the rock. So it's interesting because we can't distinguish at the macroscopic scale. So this is again the RGB frame from the microscope Leica. We don't see so much difference, but with the segmentation, after passing through the hyperspectral microscope, we see different cluster. The first one in blue, the second one in green, and the third one in red. We plot the different spectrum in front of, in function of wavelength to see if there is a difference. So between 525 and 550, we have a big increase that is dependent from the spectral signature again. So the spectral signature of the pink granite. And after 600 nanometers, we have a shift in wavelength, and it is due to different ferric ion concentration. So in conclusion, we saw that it's possible to combine both single pixel imaging, hyperspectral imaging with optical microscopy. So it is encouraging because it is functioning. The resolution power reaches 9 micrometers, with a 0.4 numerical aperture objectives. We saw that we can discriminate different elements of the sample using a spectral analysis, and we can distinguish different concentration of these different elements present in the sample. So thank you for your attention, and if you have a question, be free to ask.